Good morning to you all. I am Dr. Asima Saikia and I will be discussing today interference figures. When an anisotropic mineral is observed under convergent polarized light with both the polarizers inserted under high objective with the Barton lens inserted, we obtain a figure called as interference figure. By anisotropic minerals, we mean that these minerals are the minerals in which we have different electronic environment in different directions. As such, the ray of light on entering such minerals will be split into two rays as the slow ray. One of them will be a slow ray, the other will be a fast ray. As they interfere and they exit out of the polarizers under certain set of conditions as mentioned, with the Barton lens in, we will observe interference figures. So, we have two types of anisotropic minerals, biaxial with two optic axes and uniaxial with single optic axis, and we have different set of interference figures for uniaxial minerals and for biaxial minerals. Uniaxial interference figure and biaxial interference figures are basically used in crystallography or in optical mineralogy to determine the type of mineral an anisotropic mineral belongs to, whether it is uniaxial or biaxial, as they produce different figures, and also to check whether a mineral is uniaxial positive or negative or a mineral is biaxial positive or negative. So, how do we obtain an interference figure? For this, we observe a thin section under microscope and choose a grain and observe it under the maximum objective lens available in the microscope. After that, we will insert the condensing lens or the auxiliary condensing lens, and we will also open up the iris diaphragm and readjust or refocus the mineral all over again. Then we will insert the upper polarizer, or we will observe the crystal under cross polarizers as we call it, and we will insert the Barton lens, which will result in our observing uniaxial or biaxial interference figure depending on the type of mineral we are observing. So, in an interference figure, we have two types of structures which we usually observe. We have one set of dark cross which we call as isogyres, and we have a set of colored rings called isochromes, which are interference color rings. Depending on the type of mineral we are observing and on rotation of the stage, these figures, isogyres and isochromes, will vary. Now we will discuss about uniaxial interference figures. The first is the optic axis interference figure, as can be seen in the diagram. A mineral section cut normal to the optic axis of uniaxial mineral produce the simplest and most important interference figure. A grain with a vertical optic axis should display the lowest interference color of all grains in this sample, as this is how you will choose the grain which you will orient for optic axis interference figure. The interference figure consists of isogyres forming a dark cross, and on it are superimposed are colored rings, as you can see here, which is called as the isochromes. This dark cross is known as the isogyre, and the point where these isogyres cross cut each other, the central point, is what is called as the melatope. Melatope is nothing but the point of emergence of the optic axis. The interference color will increase in order as we move away from the melatope. Now we will discuss how these colored ring isochromes form. The auxiliary condensing lens provides a highly convergent light. As you can see, this is the auxiliary condensing lens. As a ray of light 1, 2, 3, 4, 5 are coming in, and you can see that they are getting converged on passing through the auxiliary condensing lens and is collected by the objective lens on upper sphere, as you can see. Here in between we have the sample, which is what we will study for the production of optic axial interference figure. And here it is marked is the principal section of the indicatrix. As you can see here, the ray of light 1, which is parallel to the optic axis of the crystal, hence with the ray which will not get split into two rays, will exit with the minimum retardation or zero retardation, and as such will be exiting parallel to the optic axis. But when you will see the light ray path 2, you will see that it is bending a bit and it has to travel an extra distance, and it is coming out a little bit bended upward. That is, it is experiencing a moderate retardation, and likewise the ray path following the path 3 is at a greater angle to the optic axis, so retardation is proportionately greater. Because the optical properties are symmetric about the optic axis, rings of equal retardation can be seen in an interference figure formed around the melatope, and the minerals which shows maximum birefringence will show more number of such colored rings called isochromes. When it comes to the formation of the isogyres, we will see it in this figure here. We see that the vibration direction of the light emerging from the center of a mineral or a uniaxial indicatrix, when a strongly convergent light passes through it, a mineral whose optical axis is vertical, extraordinary rays vibrate parallel to the longitude and the ordinary rays vibrate parallel to the latitude on the indicatrix on the left hand side of the diagram. Extraordinary rays vibrate along radial lines symmetric about the melatope, as you can see here, and the ordinary rays will vibrate tangential to the circular isochromes, as you can see here. This is the ordinary ray and this is the extraordinary ray. The isogyres are formed where the vibration directions in the interference figures are either north-south, as you can see here. You just follow the isogyres, you will see that either the vibration directions are east-west or they are parallel to north-south direction, which will result in a condition of extinction. The mineral is dark along these two lines, and this darkness progressively fades out on two sides of each line, and this is how we obtain the isogyres in an interference figure. The second figure which an uniaxial mineral can produce as an interference figure is the off-center interference figure. In the first case, we had seen that the optic axis is perpendicular to the direction of vibration. If the optic axis is inclined from the vertical, the interference figure will no longer be centered in the field of view. When the optic axis is within about 30 degrees of being vertical, the melatope is visible in the field of view, resulting in an off-centered figure. As you can see here, this is a kind of an off-centered figure. Such a figure we call as off-centered optic axis figure. The isogyres still form a north-south, east-west dark cross centered on the melatope that swings in an arc around the field of view as the stage is rotated, and can still be used to determine the optical character and the optic sign of the mineral. However, if the optic axis is inclined more than 30 degrees from the vertical axis, melatope will form away from the field of view, and interference figure is called as an off-centered figure, and the four isogyre arms will sweep across the microscope stage as is being depicted in this figure. If the melatope is well outside the field of view of the microscope, the isogyres sweep across the field of view in sequence as the stage is rotated, with the isogyre always remaining parallel either to the east-west crosshair or to the north-south crosshair. By noting the direction, as you can see here, it is rotating clockwise direction, here clockwise, here we have the isogyre moving in the anti-clockwise direction. We can find out the optic sign knowing the vibration directions of the ordinary and extraordinary ray in the northeast quadrant of the interference figure. As here you can see in the figures, we have the melatope which is out of field of view, which is marked in the red colors. Now we will move on to the optic normal interference figure. If a mineral grain is oriented with the optic axis parallel to the microscope stage, as you can see here, the mineral grain is oriented parallel to the optic axis, we obtain an optic normal interference figure. As these figures display maximum retardation, they are characterized by a broad fuzzy isogyre, as you can observe in this diagram above here. These isogyres occupy nearly the entire field of view when the trace of the optic axis is either east-west or north-south. On rotation of the stage by only a few degrees, the isogyre generally tends to split into two segments that exceed the field of view from the quadrants into which the optic axis is being rotated. As the isogyre appear and disappear rapidly with stage rotation, they are also known as flash figures. Now we will move on to how to determine the optic sign using the uniaxial interference figures. Generally, the optic axis interference figure is used to determine the optic sign because the vibration directions of the ordinary and extraordinary ray are known at each point in the figure. The ordinary ray vibrate northeast southwest and the extraordinary rays vibrate northwest southeast. If a land-fast accessory plate is inserted, if we see retardation, that is subtraction alongside quadrants, the mineral is optically positive. If retardations add alongside quadrants, the mineral is optically negative. Marked here in the figures you can see are regions where we have written as A, which is the addition of interference, and S, which denotes the subtraction of interference. Any kind of plate, whether gypsum plate or quartz plate, can be used to determine this optic sign using the optic axis interference figure for determining the optical sign of uniaxial minerals. Having discussed the uniaxial interference figure, we will now move on to the biaxial interference figure. The most prominent of the biaxial interference figure is the acute bisectrix figure. An acute bisectrix figure is produced if the acute bisectrix, that is X or Z, depending on the optic sign, is oriented perpendicular to the microscope stage. Given that a mineral has an optic axial angle, that is what is denoted by 2V, is less than 50 to 60 degrees, the melatopes, that is point of emergence of the optic axis, as can be seen here in the diagram, the melatopes are here, we have the isogyres here, and these are the isochromatic colored rings which we call as isochromes. This is the direction of the optic normal. Here we have the optic plane, and what we have is a vertical acute bisectrix which is perpendicular to this plane of the diagram which we are observing. The melatopes, as I have already mentioned, if they are in the field of view, an interference figure will have two isogyres which will change as the stage is rotated. Isochromes will also be visible superimposed on the isogyres. These isochromes usually form an oval shape about the melatopes, as can be observed here in the diagram. Only the right light ray that are parallel to the optic axis will experience zero retardation. Any light ray inclined to the optic axis will experience increasing birefringence, so retardation increase away from the melatopes, resulting in the oval pattern which we are observing. The pattern of isochrome remains fixed relative to the melatopes on rotation of the microscope stage. In biaxial interference figure, the isogyres form a pattern that changes as the microscope stage is rotated, as can be viewed here in this figure. If the optic plane is oriented east-west, isogyre forms a cross with the arm parallel to the trace of the optic normal, being wider than the isogyre parallel to the trace of the optic plane. The positions of the melatopes are marked by narrowing of the isogyres. If the optic plane is rotated away from the east-west, the cross-shaped isogyre split into two separate segments that will appear to pivot around the melatope. The second type of interference figure which a biaxial mineral exhibits is the optic axis figure. It is usually observed on mineral grains cut normal to the optic axis. The figure usually consists of a single isogyre at the center of which is the emergence of the optic axis. When the optic plane is parallel to vibration direction of the either of the polars, as you can see here, the optic plane is parallel to one of the isogyres in the east-west direction. The isogyre crosses the center of the field as a straight bar. As the microscope stage is rotated, it swings across the field, forming a hyperbola in the 45-degree position. What I have shown here in this diagram is actually a centered optic axis figure when one optic axis is vertical and correspondingly the second optic axis and the acute bisectrix is inclined to the vertical. The third type of biaxial interference figure is the obtuse bisectrix figure. As can be seen here, this is the obtuse bisectrix figure. It is obtained on a crystal section cut normal to the obtuse bisectrix. As the angle between the obtuse bisectrix and the optic axis, marked here, this is the obtuse bisectrix and these are the optic axis, is more than 45 degree, the melatopes will be outside the field of view. As you can see here, the melatopes are outside the field of view. The pattern of isochromes and geometry of vibration directions are essentially the same as that of the acute bisectrix figure, except in this case that the melatopes are well outside the field of view. As for the optic normal figure, or that is also called as the flash figure, it is produced when the optic normal is vertical. Here you can see that this is the optic normal which is vertical. Grains oriented to produce this figure display maximum retardation as the x and z directions in the indicatrix are horizontal. Here you can see the acute bisectrix and the obtuse bisectrix. This is the acute bisectrix. Here we have the optic axis, which are all lying horizontal, and optic normal is vertical to it. When the x and z axis are the optical directions are parallel to the vibration direction of the polars, the figure as you can see here is a poorly defined cross. On slight rotation of the microscope stage, the isogyre split into two hyperbolas moving rapidly from out of the field of view in the quadrants containing the acute bisectrix. Apart from this, we have another figure which is called as off-center figure, wherein grains and random orientations display off-centered figures whose pattern of isogyres and isochromes depends on the details of the orientation. Then we come to the point of optic sign determination using axial biaxial interference figure. To determine whether the x or z axis is the acute bisectrix and therefore the biaxial mineral we are observing is optically negative or positive can be determined using the interference figure such that the optic plane is oriented northeast southwest. For this we follow a certain steps. We first obtain an acute bisectrix figure, rotate the stage so that the trace of the optic plane is oriented parallel to northeast southwest direction. That is, the isogyres will split and move towards the northeast and southwest quadrants. If the optic axial angle is less than 40 degree, both isogyres will be visible in the field of view, and if the optic axial angle is greater than 40 degree, the isogyres will lie outside the field of view. Then we insert an accessory plate, as can be seen here in the diagram. We have inserted the gypsum plate. On insertion of the gypsum plate, a decrease in color from white to yellow, as can be seen here, indicates that the vibration direction in the interference figure, which is parallel to the optic plane, is the fast ray. This color change tells us that the ray which is vibrating parallel to the optic plane has a low index of refraction and must correspond to the n alpha, that is the retardation of the alpha ray as measured along the x indicatrix axis. Therefore, the z indicatrix axis must be the acute bisectrix. However, in the second case, an increase in color from white to blue, as can be seen here on insertion of the gypsum plate, indicates that the vibration direction in the interference figure, which is parallel to the optic plane, is the slow ray, and hence that x indicatrix axis must be the acute bisectrix. To summarize what we have studied today, we have first discussed about interference figure. An interference figure is a figure which we observe for anisotropic minerals. When we observe it under convergent polarized light, we under high objective with crossed polars, we get a figure which we call as the interference figure. Interference figures for uniaxial type and the biaxial type are different. So, we have till now studied that uniaxial interference figure can be of three types. We have optic axis figure, we have optic normal figure, and the acute bisectrix figure. Similarly, for the biaxial minerals, we have the acute bisectrix figure, obtuse bisectrix figure, optic normal figure, off-centered figure, and also a figure which we call as a flash figure. So, I will recapitulate the basic distinction between the two types of figures. We in the beginning of our class has concluded that these figures are basically used to determine whether one is uniaxial or biaxial, and secondly to determine whether it is optically positive or negative. Here I will show you in brief in two diagrams what is the basic difference between an optic axis uniaxial figure and a biaxial figure. Here we have an uniaxial interference figure wherein we have two isogyres which are constant. Here we have the melatope. These are the isogyres. And here we have the concentric colored rings, what we call as the isochromes. Uniaxial type. What is important to note is here is that we have only one melatope, two isogyres, which does not split on rotation of the microscope stage. It will move from the field of view, but it will not split into two isogyres. But in the case of biaxial interference figures, first the thickness of the isogyres are different, they are not constant, right. Then we have two melatopes, these are isogyres for case of biaxial. These are the two melatopes. You have concentric colored rings surrounding these melatopes. So these are isochromatic rings or isochromes. And the basic difference which is between these two figures is that on rotation of the microscope stage, the isogyres will split like this. You can have one isogyre or it can even form a hyperbola like this on rotation of your microscope stage. So this is the basic functionality which will allow you to distinguish between a uniaxial and a biaxial type of interference figures right upon observing the interference figure. So from these we can, if we have this kind of a figure and we insert the accessory plate where the length is fast, depending on, we have the extraordinary ray vibrating like this and ordinary ray vibrating like this. As such, we can find out which one, if there is addition of color or subtraction of color, we can find out whether the E ray is faster or the O ray is faster, and we can determine the optic sign. Similar is the case for this addition or subtraction of the birefringence or the retardation as we call it, will help us to find out about the optic sign of the mineral which we are observing for biaxial condition. So with this I conclude this class.